Good morning, students. In the last class, we discussed Huygens principle. In that, we are going to concentrate on the topic wavefront. So, what is wavefront and how it is produced? On the basis of the wavefront, the Huygens state that one principle, that is Huygens principle. By using the Huygens principle, we are going to study the reflection and refraction of the waves by the plane surface. So before going to discuss one more time, we can recall the Huygens principle. So what's the Huygens principle states? So Huygens principle. So what Huygens principle states is each point of the wavefront is a source for secondary disturbance. Is a source for secondary disturbance. Each point of the wavefront is a source for the secondary disturbance. The wave, each point of the wavefront is the source for the secondary disturbance. Wavelets, these wavelets spread in all direction with the speed of wave. So each point of the wavefront is the source for the secondary disturbance, and the wavelets spread in all the direction with the speed of the wave. The wavelets spread in all direction with the speed of wave, and these wavelets are referred as secondary wavelets. And if we draw common tangent to all the spheres or wavelets, all the spheres, we obtain the new position. We obtain the new position of the wavefront at a later time. So this is the Huygens statement, that is the principle. So each point of the wavefront is the source for the secondary disturbance, and the waves which are produced from these points spread in all direction with the speed of wave, and the wavelets are referred as secondary wavelets. If we draw common tangent to all the spheres, we obtain the new position of the wavefront at a later time. So simply the Huygens principle says if we know the wavefront at t is equals to 0, then we can find the wavefront at certain time, that is t is equals to tau. So at this time we can find the position of the wavefront. So initially we know one wavefront, after certain time we can find the position of the wavefront. For example, that is by using this principle, here is the source. So this is the primary source. From here we have one wavefront. This is the known wavefront. that is at time t is equals to 0. This one is the known wavefront. I am taking that one as a dash. So a dash is the known wavefront. So in this wavefront we have number of points. Out of these I am considering 3 points for discussing the topic. So these points acts as a source. So these 3 points acts as the source for the next wavefront. So initially at time t is equals to 0, after certain time this wavefront changes its position. To find that position, we know the formula speed is equals to distance by time. So distance is equals to speed into time. So here we know the speed. So we know the speed of this wavefront. That is, this wavefront is travel in all direction with the speed of the wave. That is, if we take this wavefront travels with the speed v, then it becomes that wavefront speed is v. So initially the time is at 0. We have to find the position when time t is equals to tau, then the distance is equals to v into tau. So tau is this small time. From this point we are going to construct one sphere, because from this point the wavelet spread in all the directions. So in all directions, that's why we are constructing one sphere of radius v into t. So the radius v into t, we are going to construct one sphere, right? So that's from here in all the direction the wavelets are spreading in all directions. That's why we are drawing the sphere in using the radius v into t. For the second point also, if we draw one sphere like this, we get like this. If we fully construct, we get one sphere. So I will take only the semi arc, right? This is for the second point, and here also we have one third point, right? For this, if we draw one sphere, we get like this. So it is at a distance of, at what distance means? It is at a distance of the radius of the sphere, that is v into t. So and last is we have to draw the common tangent to all these wavelets, that is for all these spheres, that is if I draw the tangent for all these spheres. So this one is the new position of the wavefront at time t. So this is at t is equals to tau. This wavefront becomes b dash, right? So this is the distance. At what distance it is? It is at the distance b to tau. To find the position of the new wavefront, we have to measure the distance, that is the distance traveled by this wavefront in terms of the velocity and time. So if we observe here one more tangent we can draw for this surface, we get like this. So here also we get one wavefront. This one is v into t. So this one is d dash. So from we drawing the sphere, we get two wavefronts. One is traveling in the forward direction and another one is traveling in the backward direction with the same, that is with the same distance v into t. So Huygens, he also proposed that for forward direction, the amplitude is maximum, and for backward direction backward direction, amplitude is 0, right? That is, this wavefront has 0 amplitude. So this wavefront has a maximum amplitude. That's why this one we call as secondary wavefront. Secondary wave front. So wavefront is nothing but, so here in the last class we discussed, if this one is the wave at maximum disturbances, so this one is the maximum disturbances. At maximum disturbance, we are taking that surface as wave front. Taking that surface as wave front. Only this maximum disturbance. Wherever we get the maximum disturbance, then that one we taken as wave front. So that one has the definition for the wave front. So here in the icons, the secondary wavefront, that is the new position of this wavefront, has amplitude is maximum. So amplitude is maximum, nothing but its disturbance is maximum. That's why the wavefront we call as secondary wavefront, and the first wavefront is called as primary wavefront. If we draw or if we find out the position for plane wavefront, so this one is for the spherical wavefront. If we draw same for the plane wavefront, same procedure we have to follow. So here, if we consider this one is the one plane wavefront. So here it is a dash. Somewhere here it is the source. That is, source is at the larger distance. Source is at the larger distance from the wavefront. So this wavefront is taken by the part of the sphere. This wavefront is taken from the part of the sphere. That's why it is called as plane wavefront. So here I am taking 3 points. From these 3 points, we are going to find the wavelengths. That is, we are going to draw the spheres of the distance. That is Vt. That is of the radius V into T. So if I draw, so this is the sphere for the first point, and also here we get, right? For the second point, so this is the sphere for the second point, and similarly for the third point, if you draw, so this one is the sphere. So from these points, the wavelengths are traveling in all the direction, and finally we have to draw one tangent for these 3 spheres or for these 3 wavelengths. Then we get, this one is the B dash. So B dash is the secondary wavefront. Secondary wave front, and it is at the distance V into tau, right? This is for the spherical and this is for the plane. Here, if we draw one tangent for these 3 surfaces, here we also get D dash. Here, the amplitude is 0, that's why we are not considering D dash. So, wherever we get the maximum amplitude or maximum disturbance, that only we are taken as wave front. So here is the secondary wave front. So by using this one, we are going to study the reflection and refraction phenomenon by using this Huygens principle. So first, reflection of a plane wave. So reflection of a plane wave is asked in this year for 3 marks. For 3 marks they asked for the explain the reflection of a plane wave using the Huygens principle. They ask for 3 marks. So first is reflection of a plane wave. So reflection of a plane wave by using the Huygens principle. That is how we construct the secondary wavefront. Likewise only we are studying the reflection of the plane wave. That is first we considering the plane surface. So this one is the plane surface. So this surface is the reflecting surface, because here we are going to study the reflection. So the surface is reflecting surface. So this one is the medium 1, right? Next, consider one plane wave. So reflection, we are going to study the reflection by using the plane wave. That is plane wave nothing but it's like a stride. Actually the plane means 2 dimension. So this is the plane wave. So these are the plane waves. Look. So like this they are traveling. For here we are considering plane waves in 1 dimension, that is as a straight line. So these are the plane waves which are traveling in the forward direction, right? So considering the plane wave that is traveling in the medium 1 with the speed of the wave, that is v is the speed of the wave. Speed of the wave. V is the speed of the wave. So it strikes the surface. So this one is the reflecting surface. When the plane wave is traveling like this, so if you observe here, the plane wave is traveling like this and comes and strikes the surface, right? So this one is the plane wave which strikes the surface. If I draw, we get like this. So this one AB. So AB is the incident wave front. So AB is the incident wave front which strikes the surface. That is the angle which made with the surface. That is AB strikes the surface. That angle we call as angle of incidence. That is I. I is the angle of incidence. Right? So this AB wavefront has number of points. Okay? In every wavefront, so wavefront has a number of points. For here, I am considering only the 2 points, 2 extreme points. That is at the point A and at the point B. So if observe here means this wavefront strikes this surface. That is the first point strikes the surface very early. After that, the second point, third point, fourth, fifth, sixth, and lastly, the point B strikes this surface. For in the previous, we studied that Huygens principle, the distance traveled by the point. So this point acts as a source. That is, the source B travels distance with time. So from here to here, it takes certain time. So that time I am going to take an as t is equals to time. So the B point travels with the velocity v, because the AB wavefront travels with the speed of the wave. That's why the B point travels with the speed v and it takes time t. Right, from here to here, to find out that one, the distance traveled by the B point, that is Vt. Right, from here to here, the distance traveled by the B point is Vt. So we have to find the wavefront, means we have to draw the sphere of the radius b into t. So if I draw the sphere, so this becomes the sphere. From here to here, if I draw the sphere, so this becomes the sphere. Then if I draw one perpendicular, so this distance traveled by the BC is V into T. So Vt is the distance traveled by the source B. In the same time, these points also they travel, right? For example, in the last we say here is the AA point, 1, 2, 3. These 3 points travel with the same speed, then it covers the same distance. From here to here it is Vt, from here to here it is the Vt. So these 3 points travel the same distance, then the wavefront is parallel, that is B dash is parallel. So here the incident plane is inclined. For this, here I am considering A, B. So if we observe here the 3 points like this, so if we draw the sphere for these points, so one is like this, and another one is like this, and like this. So if I draw the tangent means I get the plane like this for the inclined plane. At the point B, I get this one, but this one is the reflecting surface. We can't place these two because this one is the reflecting surface from here to here. So I get this point. For these 2 points, we cannot transmitted into the second medium. So this is the surface which separates the 2 medium due to the reflection. So these travel, that is, these are the reflected back to the same medium. That is, the distance traveled by the B point is same as that of the A point, but in the opposite direction. So if I draw from here, that is from the A point, if I draw the sphere of the distance of radius B into T, so I will get like this, right? For this is for the A point. This is for the A point. So if I draw for the second point, I will get like this. And for the third point, if I draw the sphere means I will get, and the fourth point, I will get like this. And the last point, for this point, I will get, and the last point, I will get like this, right? These are the spheres for different points because they are not, these points are not transmitting like here because they are not traveled to the second medium, they are reflecting back to the same medium. That's why the distance traveled by the B source is equals to the distance traveled by the A source, but the A source travels, that is, it reflects back to the same medium, that is, at the same distance the point A has to move back. So if I draw the tangent for these, so I will get like this. So I will erase in between middle points. So here I am considering only the first point and the last point. So if I the same distance, that is the wavelength from the source A, if I draw the sphere, and at this point we have to draw one tangent to the C. So if I draw one perpendicular from the point A, so this one is the perpendicular. and here also we are getting the perpendicular, right? So this one is A, B. So AD represents what? The reflected point, that is the distance from A to D, because in the medium one we have the same velocity v, and the source, which are the points which are in the plane, all are traveling with the same time. Then from A to D it equals to v into t. The distance traveled by A to D is vt, because in the medium one we have the velocity, or we have the speed v. So this is for constant in the medium 1. So the distance traveled by the B point is equals to the distance traveled by the A point, that is A source. Here it not transmitted into the second medium, but it reflects back to the same medium. Then we get the distance Vt, which we draw the sphere of radius Vt. Then we get one wavelet. From that we have to draw one tangent to meet the point C. Then the DC represents reflected wave front, right? So this one, angle I is the angle BAC, that is equals to angle of incidence I. So if you observe, this wavefront will come. So the wavefront will come like this and strikes the surface. Later it travels like this, means it has to reflect the point B. So this one is very small. Next, the angle of reflection. Here, this is the reflected wavefront. Then this angle is the angle of the reflection. So angle BCA is equals to R, then it is angle of reflection, right? So this is how we constructed the reflected wave front. That is, every wavefront has number of points. So number of points travel with the same speed. If the point B travels with v, then point A is also travels with the v speed, and it takes the time t. They also it takes the time t only. But here we are studying the reflection. It not transmitted into the second medium, then it bounces back to the same medium. Then we draw the or we draw the sphere of radius v into t. Then we draw the tangent from point D to C. Then we get the reflected wavefront, and R is the angle of reflection. Now we have to prove the loss of reflection, right? If you observe the triangles, from triangle A, B and C, from triangle A, B, C and triangle A, D, C. So if you observe these two triangles, the angle B is equals to angle D, that is equals to 90 degree. That is, angle B is equals to angle D, that is equals to 90 degree. Then if you observe, the base AC is same for these two triangles, then AC is same. So AC is same base for two triangles. Then these two triangles are said to be congruent triangles. Congruent triangles, right? So these two triangles can say congruent triangles, because angle B is equals to angle D, that is equals to 90 degrees. That is, two angles are same and the sides are same for two triangles. That is, AC side is same for these two triangles. Then that these two triangles, we are saying that these are the congruent triangles. So from congruent triangle, the other angles, the angle angle BAC is equals to angle DCA. From the congruent triangles, this is from the geometry. From congruent triangles, the angle BAC is equals to angle DCA. Then the angle BAC is I, angle of incidence. That is I, that is equals to angle DCA. Sorry, here it is. DCA. So angle DCA is angle R, right? So the law of reflection says that angle of incidence is equals to the angle of reflection. So we studied the reflection by using Huygens principle, right? So in this year only, that is March 2020, they asked this question for 3 marks. Explain the reflection of a plane wave using the Huygens principle. So this is asked for 3 marks, right? So here we are considering one wavefront like this. So it incidents onto the surface, then after incident, the first point A incidents first to the surface. Later, the point B, the B point travels the distance, that is VT. Then the same A point reflected back to the same medium into the distance V into T. Next, by constructing the wavefront DC, by using this Huygens principle, we constructed the reflected wavefront DC. At every point, we draw in the spheres and we draw the tangent to that wavelets. We get the reflected wavefront, that is DC, and the angle which makes it to the surface is the angle of reflection. From the geometry, that these two triangles ABC and triangle ABC, from observing these two triangles, the angle D and angle B is 90 degree, because here we are drawing the normal. Next, the base AC is same for the two triangles, hence we said that these two triangles are congruent triangles. From the congruent triangle, we can say angle BAC is equal to angle DCA. Hence, we know BAC is the angle of incidence and DCA is the angle of reflection. That is, I is equals to R. So this is the law of reflection. Already we studied in the ray optics. So here we are studying the reflection by using the wave. That is plane wave. Next, we move on to the topic refraction of the plane wave. Right? So next is refraction of a plane wave. That is, in plane wave we are considering the plane wave front. So if I draw here, this one is the incident wave front, and if I draw here is the reflected wave front, right? So here we are going to study the refraction by using the plane wave. So here also we are considering one surface. So this surface separates the medium. So this one is the surface. So this surface separates the medium, that is medium 1 and medium 2. We have two mediums separated by the surface. So here also we are considering one plane wave, that is plane wavefront, which is traveling from the medium 1. So here we have two mediums, then we have two velocities. So v1 is the velocity in medium 1 and v2 is the velocity or speed in medium 2. So v1 and v2 are the speed in medium and 2 respectively. So v1 and v2 are the speeds in medium 1 and medium 2 respectively. That is v1 in medium 1 and v2 in medium 2. So if we consider the speed v2 is less than v1, so what happened? So consider one plane wavefront, that is A, and here it is B. So this plane wavefront has number of points. So here we are considering only the extreme points. So the point A strikes the surface at first, and after some time the point B strikes the surface. That is, if the source B takes the time to strike the surface is T, that is T is the time, then it travels with velocity or speed. It travels with the speed, that is v1 is the speed in the medium 1. Then if we draw the sphere of radius v1 t, so the sphere is radius, that is distance traveled is equals to v1 t. So if I draw the sphere means, then the distance traveled by BD. So this one is the BC. This is V1T. So here the time taken by the source B to strike the surface is T. It's traveling with the velocity V1. In the same way, here the A point also travels with the same time as that of B. So here the B source travels 5 seconds, then here the A source also travels 5 seconds. So this one is angle of incidence I, right? But here the speed changes because it transmits from medium 1 to the medium 2. Then the distance traveled by the source A is B into T. Here the time taken by the B source is same as the time taken by the A source. So if I draw to find the distance traveled by the source A, then we have to draw the sphere of radius V2 into T. Then I get the sphere like this. Then if I draw the tangent from this point to point C and also one perpendicular to here, then this point becomes point D, right? So this angle ACD is the angle of refraction, that is it transmitted into the second medium. So this angle R is the angle of refraction. If I observe the distance AD is less than that of the BC, because the AD travels with the speed V2, here the BC travels with the speed V1. So here the distance AD is V2T, that is BC is equals to V1 T and AD is equals to V2 T. If I observe here the length, if I observe the length BC is greater than the length of AD, because in the second medium the particle A, that is the source A, that is the point A of the wavefront AB, travels with the speed V2. That's why it covers lesser distance than that of the source B. For example, the time T for these two cases, if I take 5 seconds and V1 as the velocity or speed V1 is equals to, in the medium 1 is 10, then the distance traveled is 50 meter. If it is meter per second, then the distance traveled is 50 meter. Then if I take the time is same, then here it is 5 seconds. If the velocity is less in the medium 2, that is if I take 5 meter per second, then the distance traveled in the second medium is 5 into 5, 25 meter. So if I observe 50 meter, that is the distance BC, is greater than the distance AD, that is 25 meter. In these two cases, the time is same because all the points are travel with the same time. If B travels with T, then A also travels with T. In between here somewhere we consider one point, so that point also travel with the same time T, right? Then from triangle, so here this one is 90 degree and here it is 90 degree because we are drawing the perpendiculars. So from triangle, ABC, from triangle ABC, sine I, that is equals to opposite side by hypotenuse. So opposite is BC and the hypotenuse is AC, right? So sine I, we know the value of BC is V1T divided by AC, that is sine I. So from triangle ADC, so these two are the right angle triangles. Then we have angle sine R. So this is the sine R. So sine R is equals to opposite side by hypotenuse side. So opposite is AD and the hypotenuse is AC. So this can be written as, we know the value of AD, that is V2T divided by AC, right? So sine I is written equation 1 and sine R equation 2. So here we are proving the laws of refraction. So if we divide sine I by sine R, that is equation 1 divided by equation 2, sine I by sine R, then V1T divided by AC, V1T divided by AC whole divided by V2T divided by AC. So in the denominators of these two terms, AC is common, we cancel those two terms, then we get sine I by sine R, that is equals to V1T by V2T. Here we already said that T is same in both the mediums, then TT get cancelled, we get V1 divided by V2. That is sine I by sine R, that is equals to V1 by V2. Right? If the angle of refraction R is less than to the I, then V2 is less than V1, because here if we observe this value is less, then I is greater, that is equals to V1 by V2, then V2 is less than to the of V1. That is, angle of refraction is less, then the speed in the second medium is less. If angle of refraction is more, then the speed is more than to the first medium, right? Sin by sin R. So we know. So we know refractive index of medium N1 is equals to C divided by V1, and refractive index of the second medium, that is equals to C divided by V2. Absolute refractive index of the first medium and absolute refractive index of the second medium. So here we get sin I divided by sin R, that is equals to V1 by V2. So if we replace the value of V1 for the refractive index, then it becomes C divided by N1. V2 becomes C divided by N2. So in the numerator and in the denominator, C is common, then it gets cancelled. So the remaining is N2 divided by N1. That is sin I divided by sin R. So this is the Snell's law. So sin I by sin R is equals to N2 divided by N1, right? So this is the law of refraction, that is Snell's law. So we prove the Snell's law by using the plane wave. When it strikes the surface, we get sin I divided by sin R, that is equals to N2 divided by N1, right? Next. So here we are studying the wave, then the BC becomes the wavelength. BC becomes the wavelength in the medium 1, that is lambda 1. BC is equals to the length of BC, that is lambda 1. Lambda 1 is the wavelength of BC, that is we are studying the wave. The length of the wave is the wavelength, that is BC is equals to lambda 1, and here for AD it is lambda 2. So if we substitute these values here, for BC we have V1T, that is V1T is equals to lambda 1 and V2T is equals to lambda 2. If we divide these two, lambda 1 divided by lambda 2 is equals to V1 by V2, right? So if we rearrange lambda 1 by V1, that is equals to lambda 2 by V2, that is equals to constant, right? So from this, if the wavefront travels from one medium to the another medium, its wavelength and its speed changes. From this we say that wavelength and speed changes, but frequency remains constant. Frequency remains constant, right? So this is about the refraction of a plane wave when it travels from the rarer medium to the denser medium. In the next class, we will discuss from denser to rarer medium and total internal reflection and refraction takes place in prism, mirrors and in lenses. So in the next class, we will discuss the plane wave, how the changes when it travels through prism, mirrors and lenses. Thank you.